Okay, so here's another function definition, and this one looks a little bit different. You can see that we've got this alternative f of x notation, but that doesn't spook us. We know that's just another way of writing y equals or f of x equals. It just means the same thing. But this function has two parts to it. So for x values less than 1, one rule applies, and for x values that are 1 or bigger, a different rule applies. This sort of function is called a piecewise defined function. Very pompous, isn't it? There you go. But it's just an example of a function where, depending on the number that you're putting in, you may have to vary the rule that you apply. And you know, there are some material, the chemists amongst us know that some materials behave some way at certain temperatures, and then they behave differently at other temperatures. So water, for example, when x is less than or equal to 1, behaves in one way. If x is the temperature, it behaves in one way, and then if x is greater than 0, where x is the temperature, water behaves in a different way. And then, of course, you've got a third situation where x is greater than or equal to 100, and water behaves differently again. So there are lots of situations where the value that you put in doesn't always get have the same function applied to it. And it's important to note that if x is actually equal to 1, this rule applies. So go on, have a go at sketching that function. So basically you've got to sketch the two functions on one set of axes, but this one only applies that side of x is 1, and this one only applies that side of x is 1. Have a go. Sorry, I've just done this without the video showing, so I apologise. So the first function is valid until x is 1. When x is 1 in the first function, you get y is 3. So this comes all the way down to, but doesn't actually reach 3. So we have an open dot to show that it can't actually be equal to 1, 3. The second function, when x is 1, gives us 4. So the function continues up here, and it can be equal to that value, so it continues up there. So we get this really rather odd shaped function at the range. So do you remember we said, right, these are the numbers we put in, these are the numbers that come out, the numbers we put in are called the domain, and there's no limit. There's no limit on the domain. X can be less than 1, and it can be 1, and it can be bigger than 1. So that's good because it means that this is a function. And the range, well, those are what y values do I get? Well, I get any y value above 3, but this is crucial. I don't actually get 3, so f of x is greater than 3. Remember what we were saying yesterday? We would say that, not yesterday, day before, y is 3, that actually we really ought to say the range in terms of f of x. And so the second part of that question, solve f of x equals 19, that's basically saying, when does y equal 19? And I can see from my graph that it's going to happen twice, isn't it? So, not to scale, this next bit, but if that's 19, there's a point there, and there's a point here. So A is where the straight line equals 19, and B is where the parabola equals 19. So x is minus 7 makes sense for A, doesn't it? Now x squared is 16, so x could be plus or minus 4. But of course, this function is, or this part of the function is only valid when x is greater than or equal to 1. So I'm not going to do plus or minus 4. There's clearly only one place where that line crosses 19, and that's going to be when x is 4. So a piecewise defined function is a function where different rules apply for different values. Let's just do one more example, and then oh no, we're not going to do one more example. We're going to move straight on to the exercise. So for those of you at home, we're on page 31 and 32 in the Pure 2 textbook, and we're going to do question 6 onwards. Cheerio. So question 6 here, is anyone able to suggest why g is not a function? What do you say?
Substitute 4.
Yeah, it's not defined for x is 4. Sorry, you're going to say the same? Yeah, it's not defined for x is 4. And for it to be a function, it's either got to be 1, 1 or many to 1. Well, there's no problem with that. But it's got to be defined for every value, so not a function. So f of x, I've sketched the two graphs sort of normally. When x equals 4, the first graph is 0. So this is going to come down to 4, but of course it can't be 4. So it's going to look like that. And with the second function, when x is 4, you get 16 plus 9, you get 25. Sorry, not to scale. All right, so we've got up there 25, and that's a solid dot. So my parabola disappears there. F of 3, what happens when you put 3 in? F of 10, what happens when you put 10 in? Make sure you're putting it into the right half of the function. And this is just asking when does y equal 90. Hopefully, again, you can see there'll be two solutions to that, because this graph carries on up forever, and that one carries on up forever. I'll give you a few minutes. Once you've done 6, then crack through with 7 and 8. And then I had suggested, actually no, sorry. Yeah, no, 7 and 8. Yeah, 7 and 8. So when f is 3, we put it into the top function. 4 take away 3 is 1. When f is 10, we use the bottom function. 100 plus 9 is 109. Where does that function equal 90? Well, y is 90 is up here, so both lines will cross that. So I just have to ask, when does 4 minus x equal 90? And that's where the minus 86 comes from. And also, where does x squared plus 9 equal 90? And again, the answer to x squared is 81 is plus or minus 9, but this function is only defined for values greater than 4, so that's why the answer is just 9 there. Okie dokie. So we yesterday went through 2 composite function examples, and here's a third. So with a couple of exceptions, I'm hoping that you sort of got your notes from yesterday and you can remember that this notation here means we're going to take 3 and put it into the function g first, and then whatever comes out of that is the number that we put into the function f. And ignoring the equals x, that notation there means what algebra do you get if you take x and put it into g, and then whatever comes out, you put that into f. And the only difference here is that one of our functions uses modulus notation. So we know that we're going to put a number into this function, but whatever number comes out, whether it's positive or negative, we're just going to write it as a positive number. So just to warm yourself up, take number 3, put number 3 into G, and then whatever comes out, put that number as x into f. And then see if you can do the algebra. Actually, the algebra one, it works out quite nicely. It's not a nasty one at all. So when I put 3 into G, 3 plus 1 is 4 divided by 2, 2 comes out. So 2 is the number I put into F, 2 lots of 4, 2 lots of 2 is 4, take away 8 is minus 4, but it's the modulus of that, so it's 4. If I put X into G, I get x plus 1 over 2 comes out, sorry. If I then make that my x in f, what I get is 2 lots, this I replace with that. The thing that came out of G. And of course 2 lots of something divided by 2 is just, sorry. So that is fg of x. Except it doesn't just say find fg of x, but it says solve fg of x equals x. And remember I said we use graphs with modulus problems to solve equations just like this. This is an example of a modulus equals algebra question. So we're going to solve it by sketching y equals the modulus of x minus 7, which I hope you can do really easily now, and y equals x, which I'm also hoping you can sketch the line of. So on, you might want to grab a whiteboard or in your book, see if you can sketch those 2 lines. Remember, the modulus of x minus 7 will be a bounced one, whereas y equals x isn't modulus, that's not going to bounce. And we're just looking for where the 2 lines cross. So here's the y is x minus 7 line, which will bounce when it's the modulus. And here's the y equals x line. Crucially, these 2 lines have the same gradient, so we've only got one solution. And that's when y equals x crosses the bounced part of that line. So the original line was x minus 7, so the bounced part is minus x plus 7. So the solution is x is 7 over 2 or 3.5, and just one solution. So we are on page 34 in the textbook, and for the rest of the lesson we're just going to be starting at question 3 and working through those questions there, starting with this one.